In this video, I'll be working examples 7, 8, and 10 from section 12.3. Note that in section 12.3, you're learning how to differentiate compositions of functions, whereas in section 12.2, you learned how to differentiate products and quotients. So take some time to review the rules of compositions, learn the chain rule. There's a couple of presentations of the chain rule in this section. And when you get ready to work example 7, restart the video so that we can work it together. In example 7, we're not only going to be practicing using the chain rule, but also the product rule. So this is a great problem. Find the derivative of y equals 4x times 3x plus 5 to the 5th. We can call the derivative y prime, among other things, dy over dx or y prime would be sufficient. Noticing that we're dealing with the product of two functions of x, we're going to start with the product rule. So we have the first function, 4x, times the derivative of the second function. Now notice the second function is the composition of two functions. That means one function is plugged into another function. You have a linear function here plugged into a power function. So when we differentiate that second function, we're going to have to apply the chain rule. So starting with our power rule, we take the power down in front as a coefficient, and then we decrease the exponent by 1. Now be really careful here. Keep the base the same until you complete that power rule. So again, we saw the exponent come down in front as the coefficient, the original exponent decreased by 1, and the base stayed the same. Now the chain rule says, since there was something other than just an x in parentheses, we also have to multiply by the derivative of that base. So that completes the derivative of the second function. But don't forget, we were in the midst of the product rule. So we have another term to evaluate for the product rule. Now let's look at the pattern. We have the first function, first, times the derivative of the second, plus, now we're going to do the derivative of the first times the second. So we need to calculate the derivative of our first function there, which is 4x. Well, that's a lot easier than the first round, right? The derivative of 4x is just 4. And then we keep the second function as is. So we have first times the derivative of the second, which requires the chain rule, plus the derivative of the first times the second. So we executed the product rule. That was our overall plan. And within the details of the product rule, we had to apply the chain rule. At this point, the calculus is done, and now we need to simplify. So looking at the first term on the left of that big plus sign, we've got several terms that we can multiply together. If we do 4x times 5 times 3, let's see, 4x times 5 is 20x, and 20x times 3 gives us 60x. And then we have this factor, 3x plus 5 to the 4th. And the second factor looks good as it is. Now, I don't really feel like taking 3x plus 5 to the 4th power and multiplying it all out, nor 3x plus 5 to the 5th power. So instead of multiplying everything out, let's simplify by factoring. So notice we have two overall terms here. There's my first term, and there's my second term. I want to determine their greatest common factor. So let's look at the little factors first. You've got 60x on the left and 4 on the right. The greatest common factor between 60x and 4 is 4. Now let's look at the bigger factors. You have 3x plus 5 to the 4th and 3x plus 5 to the 5th. What they have in common there is the lowest power, 3x plus 5 to the 4th. So that's our greatest common factor, and we're going to extract that from both terms of the derivative. Now I'm going to think, what can I multiply 4 by in order to get 60x? Well, that would be 15x. And notice 3x plus 5 to the 4th from the extraction of the GCF, that exactly matches the 3x plus 4 in that first term. So when I multiply those two together, I end up with the original term. Okay, now let's take the GCF out of that second factor. I notice that the second factor already has the 4, which matches my GCF. But I noticed that I need 3x plus 5 to the 5th, whereas my GCF only has 4 of those. So I'm going to need an extra 3x plus 5 to the first power. Now, since we factored, let's double check by distributing our GCF. So if I take the GCF and I distribute it to the first term, multiplying those would give me 60x times 3x plus 5 to the 4th power, which matches my original first term. When I distribute it to the second term, I'd end up with 4 times 3x plus 5 to the 5th power. Remember, when you're multiplying like bases, you add the exponents. So that takes care of that term. So it looks like we have factored it correctly. The only thing that we have left to do is to simplify what's in brackets. So let's do that. We have our first few factors here that I'm just going to copy down. We're going to demote those brackets to parentheses. And notice, when I drop parentheses after this plus, we're going to have like terms. 15x plus 3x, that would give us 18x, and we still have a plus 5 there on the end. Everything's completely factored and simplified, so we have successfully found the derivative. On example 8, we're also going to have to apply a combination of rules. Now, just looking at the function, the main overall structure there is that it is a quotient. So I'm going to have to apply the quotient rule. But when I get ready to differentiate the numerator, I notice it's the composition of two functions. So on that little detail of the quotient rule, we'll apply the chain rule. So find the derivative with respect to x of our function. Let's work on our quotient rule. It's a good habit on your quotient rule to begin by squaring the denominator. Remember, that reminds us to lead with that term in the numerator so that we get all of our terms in the right order. So we have the numerator begun, x minus 1. Now we want to multiply by the derivative of the original numerator. So here's where the chain rule comes into play. I begin with the power rule. That is, we bring the power down in front as a coefficient. We keep the base the same and decrease the exponent by 1. But because we had something other than just an x under that power, the chain rule says we also multiply by the derivative of the base. So there's the first half of our quotient rule. Also remember, in quotient rule, there's a minus between the two terms, whereas it was a plus in the product rule. So let's see where we are in our quotient rule. We have the denominator times the derivative of the numerator. So next, we need the derivative of the denominator times the numerator. So we are going to work on the derivative of the denominator. Well, that one's easy. The derivative of x minus 1 is just 1. Then we multiply by the original numerator. And the quotient rule is complete. The chain rule was part of it, so the calculus on this problem is done. We're going to finish out with algebra. And our goal is to simplify this function. So let's just drag our denominator along here, x minus 1 squared, and work on this first term to the left of that big minus. So I'm going to multiply these little terms. 7 times 3 is 21, and bring that to the left. And then we have binomial factors x minus 1 times 3x plus 2. For that second term, I'm just going to omit that coefficient of 1 and call it minus 3x plus 2 to the 7th. Now, I really don't want to multiply out 3x plus 2 to the 7th. So like we did on the previous problem, let's factor out the GCF between the two terms in the numerator. So looking at our two terms, now just to be clear, this is my first term, this is my second term. I want to find out what they have in common. Well, they both have a 3x plus 2. So we're going to extract that as a GCF and see what's left. If I divide 3x plus 2 out of that first term, that leaves behind 21 times x minus 1. If we divide 3x plus 2 out of that second term, we end up with 3x plus 2 to the 7th power. Hold on, I'm missing something, aren't I? Did you catch that? Here, let's go backtrack a little bit. Did you notice this was a 6? That should be a 6 right there. So what these two have in common is 3x plus 2 to the 6th. Better? Okay, I hope you were paying attention and caught that. Make sure you correct that on your paper. So at this point, let's double check. 3x plus 2 times to the 6 times 21 times x minus 1, that gives me my correct first term. And then 3x plus 2 to the 6th times 3x plus 2 to the 1st gives us 3x plus 2 to the 7th. Okay, we are back in business. Now we need to divide by denominator squared. The last thing we need to do is simplify what's in brackets here. So we'll distribute our 21, we'll distribute our negative, and then after that we'll combine like terms. So we have 3x plus 2 to the 6th power times, demote the brackets to parentheses. We have 21x minus 21 minus 3x minus 2. We can simplify that second parenthetical element. 21x minus 3x gives us 18x. Negative 21 minus 2 gives us minus 23, all divided by x minus 1 squared. All right, we had kind of a close call there, but we ended up with the right answer. Go ahead and take some time to pause the video, work example number 9, and when you get ready to work example number 10, you can restart the video and I'll work through it with you. Example 10 says, suppose a sum of $500 is deposited in an account with an interest rate of R% per year, compounded monthly. At the end of 10 years, the balance in the account is given by A equals 500 times 1 plus R over 1200 to the 120th power. Find the rate of change of A with respect to R if R is 5 or 7. So let's translate the English into math. We want the rate of change, that says derivative, of A with respect to R. That means we want to find A prime of R. We're going to differentiate this function A with respect to the variable R. So the first thing I notice is that we have a constant coefficient of 500. That constant coefficient filters through to the derivative. Then we need to apply the chain rule to this part. We have a function raised to a power. So we want to think about the power rule first. We bring the power, 120, down in front as the coefficient. Remember, we keep the base the same at this point in the problem and decrease the exponent by 1. Then the chain rule says, because the base was something other than just an R, we need to multiply by its derivative. Well, the derivative of 1 is 0. Thinking of R over 1200 as the constant 1 over 1200 times R, the derivative is just that constant 1 over 1200. We can take some time to multiply out all of our numbers. We can evaluate 500 times 120 times 1 over 1200. Now, just to be sure I don't mess that up, I'm going to use my calculator to evaluate that. So we have 500 times 120 times 1 divided by 1200. And that gives us a new constant of 50. So I can simplify this as 50 times 1 plus R over 1200 to the 119th power. That's my derivative. The problem says, find the rate of change of A with respect to R if R is 5 or 7. That simply means we need to evaluate A prime of 5. So we're plugging 5 in for R in our derivative function. That's 50 times 1 plus 5 over 1200 to the 119th power. And then, when we're done with that, we can calculate A prime of 7. So we have 50 times 1 plus 7 over 1200 to the 119th power. So let's evaluate that with our calculator. We have 50 times 1 plus 5 over 1200. Make sure you close parentheses here, type your exponent key, 119. And then we'll evaluate it. If we round to 2 decimal places, we get 82.01. So our first answer here 82.01. Now that I have that typed into my calculator, I can do a little shortcut and have the calculator recall everything I just typed in. I can type the second key and enter. Second entry, again, recalls everything that I just typed in. And then, just going to use my arrow keys to change that 5 to a 7 and press enter. 99.90 in this case. So 99.90. So if R equals 5, the rate of change is 82.01. Now remember what we were looking at here. A is the balance in the account, and we looked at the derivative of A with respect to R. So the rate of change of dollars with respect to percentage point. If R equals 7, the rate of change is 99.90 per percentage point. I hope these videos are helpful. Remember, you can always contact me by email if you have any questions.